All right, let's just jump right in. Welcome to This Explainer, where today we are unpacking one of the most elegant, universal, and honestly, quietly powerful ideas in all of physics. We're talking about an idea so beautifully simple that a kid throwing a rock in a playground is basically demonstrating it, yet it's so profoundly deep that it took humanity nearly 2,000 years to actually figure it out. Today, we're exploring the hidden mathematical architecture of projectile motion.
So, I want you to think about this for a second. What does a skipped stone, a baby's spit up, and the moon silently orbiting our planet actually have in common? I know, it sounds like the setup to a really bizarre joke. But physics? Well, physics honestly doesn't care about dignity. It only cares about forces. And by the end of our journey today, you're going to see exactly how these wildly different things are bound by the exact same mathematical rules. We're going to go from the messiness of everyday reality straight to the wonders of the cosmos.
Okay, let's get our foundation set. What exactly is a projectile? In the language of physics, it's any object that's been launched, thrown, or shot, and then left to travel through the air under the influence of gravity alone. That right there is the critical phrase, gravity alone. Think about it. Once a basketball leaves a player's hand or a cannonball leaves a barrel, there's no engine pushing it forward anymore. In a perfect, idealized world, the only thing acting on that object is the invisible, relentless downward pull of the Earth.
Now, the grand secret to this whole phenomenon, which was actually first formalized by Galileo, is that the motion of a projectile can be cleanly split into two entirely independent problems. Think of it like two totally separate movies playing on top of each other at the exact same time. Horizontally, there are no forces acting on the object, so it just cruises along at a constant, unchanging speed. But vertically, gravity is constantly pulling it downward, increasing its speed by 9.8 meters per second every single second. And the crazy part is, these two motions do not interfere with each other at all. To really see this counterintuitive reality in action, just picture yourself standing on a rooftop. In one hand, you drop a ball straight down. At the exact same instant, with your other hand, you throw a second, identical ball perfectly horizontally as hard as you possibly can. Which one hits the ground first? Astonishingly, they hit the ground at the exact same moment. That massive sideways push you gave the second ball has absolutely zero effect on how quickly gravity pulls it downward. They complete their vertical fall in identical time. No way, right? But it's true. Now, believe it or not, this complete independence of horizontal and vertical motion wasn't always obvious. For roughly 1,700 years, humanity was stuck on Aristotle's heavily flawed impetus theory. He actually incorrectly argued that air rushed behind a thrown spear to physically keep pushing it. It wasn't until 1537 that an Italian mathematician named Tartaglia finally chipped away at this, founding modern ballistics. And then finally, in the early 1600s, Galileo used these incredibly careful rolling ball experiments to cut through the confusion entirely, proving that the true path of a falling object is a continuous, mathematically perfect curve called a parabola. That turning point in 1537 with Tartaglia was absolutely massive. Through incredibly careful observation and calculation, he made a foundational discovery that is still incredibly useful today. He figured out that if you want to achieve the maximum horizontal range on perfectly level ground, you must launch your projectile at exactly 45 degrees above the horizontal.
And what's really fascinating here is the beautiful mathematical symmetry hiding within this idealized rule. Because of the way the trigonometry works out in the range formula, launching at 30 degrees gives you the exact same distance as launching at 60 degrees. 20 degrees pairs perfectly with 70 degrees, 10 pairs with 80, they all mirror each other perfectly, but 45 degrees stands completely alone at the absolute peak. But, and this is a very big but, all of this perfectly clean symmetrical math relies on one massive glaring assumption, that we are completely ignoring air resistance. So here comes the messy plot twist. In the real world, air resistance, or drag, isn't just some minor detail you can casually brush aside. It's a complex, non-linear force that fundamentally ruins that perfect parabolic curve. As an object physically pushes through the air, the resistance it faces grows dramatically as its speed increases. Actually, get this, if you double an object's speed, the drag force pushing against it roughly quadruples. To put that into perspective, just look at how catastrophic air resistance is to our perfect math. If you take real baseball data, a 90-mile-per-hour fastball launched at that ideal 45-degree angle in a perfect vacuum would travel an enormous 163 meters. That's huge. But when you factor in the actual air drag pushing against the baseball surface, that range plummets to just 95 meters. That is a 42% reduction. This is the exact reason why outfielders can easily catch fly balls that, according to textbook math, absolutely should have been towering home runs.
So the reason different objects react so differently to all this drag all boils down to the ratio of their surface area to their mass. Take a badminton shuttlecock, for example. It has a massive surface area, but very little mass, right? So its path gets violently distorted by the air. On the absolute opposite end of the spectrum, you have a heavy, compact cannonball. It basically just ignores air resistance altogether, slicing right through the atmosphere to trace out a near-perfect parabola.
Okay, but drag isn't the only aerodynamic force at play here. Introduce spin to the equation, and you get an entirely different magic trick. When a projectile is spinning as it moves through the air, it literally drags local air molecules along with its surface. One side of the spinning ball speeds up the local air, which creates a zone of lower pressure. The other side fights the air, creating higher pressure. And this pressure difference actually physically pushes the spinning ball sideways. In physics, we call this the Magnus effect. Athletes practically weaponize this physics to completely manipulate a ball's flight path. It's wild. In baseball, a pitcher will use topspin to make a curveball drop incredibly sharply, or backspin to create the crazy illusion of a rising fastball. In soccer, players strike the ball with heavy sidespin to bend a free kick cleanly around a defensive wall. And in golf, the very reason golf balls have all those dimples is to grip the air, working perfectly with backspin to generate massive upward lift, allowing the ball to fly significantly farther than a smooth one ever could.
This effect actually has a remarkably surprising historical timeline too. Isaac Newton himself was the first to correctly observe it way back in 1671 just by watching college students play tennis at Cambridge. But perhaps its most creative and frankly devastating application came centuries later, during World War II. The Royal Air Force engineered these incredible bouncing bombs with heavy backspin. This Magnus effect allowed the bombs to literally skip across the water surface, completely bypassing torpedo nets to strike German dams.
All right, now let's zoom out, way out, to a profound cosmic scale. In 1728, Isaac Newton proposed a breathtaking thought experiment. He imagined standing on an impossibly tall mountain, a peak so high up that it extended completely past the Earth's atmosphere, eliminating our messy air resistance entirely. And from this peak, he imagined firing a cannonball perfectly horizontally. So, here is the mind-bending realization. If you fire that cannonball at a modest speed, it just arcs down on a standard parabola and hits the ground, right? But remember, the Earth is a sphere. The ground is constantly curving away from you. So, what if you fire it so fast that the rate at which gravity pulls it downward exactly matches the rate at which the Earth's surface curves way beneath it? It would fall perpetually, forever missing the ground. It would enter an orbit. Fire it with even more extreme speed, and it overcomes gravity entirely, escaping off into deep space. That delicate, totally perfect balance happens at a very critical number, 7.9 kilometers per second. If you can launch an object at exactly that speed, purely horizontally, completely above the atmosphere, it falls at the exact same rate the Earth curves away. It simply becomes a satellite. And this is the grandest unification in classical physics. There is absolutely no fundamental physical difference between a rock casually tossed by a human hand and the moon orbiting silently around our planet. None. They are both simply falling under the exact same universal force of gravity, governed by the exact same mathematical rules. The only difference? Horizontal speed. So the next time you step outside, I seriously want you to just look up. From a child's simple game of catch, to the International Space Station, to the moon itself, it is all just projectile motion. It's kind of amazing when you think about it. What else around you is just a falling rock in disguise? Thank you so much for joining me for this explainer. And hey, keep noticing those parabolas all around you.